Yeah, you can start.
So thank you, Professor Hossein. Dear everybody, it is with deep humility and sincere gratitude that I will deliver this honorable lecture. Over the past, not 35, 38 years of my research in steels, the person who most profoundly influenced my thinking was Professor Tadashi Maki, Kyoto University. His guidance, rooted in the philosophy of understanding the heart of steel and engaging in dialogue with it, was more than a metaphor. It was a compass that shaped the very foundation of my research. Throughout this journey, I have had the privilege of meeting and learning from esteemed colleagues around the world, whose genius advice and inspiring discussions have greatly enriched my work. I'm particularly grateful to Professors Yo Tomota, Setsuo Takaki, Kaneaki Tsuzaki, Masato Enomoto, Peter Hodgson, John Will Morris, Harry Badesha, Derek Rabe, Peter Voorhees, Doug Ponge, Dorna Dorote, Beradi Hossein, Elena Pereloma, Elena Timokihina, Don Uso, and Professor Toshihiro Tsuchiyama. Beyond the field of metallurgy, I have also been deeply inspired by researchers in mathematics, biology, and computer science. Their interdisciplinary perspectives open new dimensions in my thinking. Equally important has been the stimulation and the joy I have received from working closely with my students, whose enthusiasm and curiosity constantly reminded me why research is a lifelong pursuit. As I continue along the path of scientific inquiry, I remain committed to listening to the voice of steel and to devote myself to the understanding its mysteries with sincerity. I also hope to support and encourage the next generation of young researchers who share a deep passion for steel. Finally, I would like to express my profound respect for the field of steel research itself, which has nurtured me throughout my career. So today, I will talk about the digital transformation of steel material research, a journey toward better understanding the inner nature of steel, and a tool to help us connect with what materials are feeling. I have worked across academia and industry, and I hope to share some cross-disciplinary insight with you today. Here is an overview of today's my talk. First, I'll discuss what keeps us motivated in long-term steel research. Then I'll explore how computers now support us in seeing, diagnosing, creating, and even designing materials. The first topic is the sustaining motivation in steel research. I often pose a somewhat poetic question. What if we could think like steel? This mindset helps us ask fundamental how and what questions. It's also a powerful source of motivation to sustain research over decades. In the field of thermodynamics and crystallography, many brilliant researchers have already made great progress. Their work has laid a very strong foundation. Instead of following those well-established paths, I've been more interested in somewhat a little different, the quantification of microstructures. I learned a lot from Professor De Hoff's excellent textbooks on quantitative teleology, which really shaped my thinking early on. For the past 38 years, my research has been driven by a simple goal: to quantify steel microstructure in more depth, and in doing so, to get just a little closer to understanding what steel is feeling. In other words, to grasp its inner nature through numbers. Logically linking process, microstructure, and properties lies at the heart of materials engineering. However, conventional approaches to establishing these relationships through experiments and simulations have traditionally been extremely time-consuming. Moreover, while process and properties can usually be expressed numerically, microstructures are often represented as image, making it inherently difficult to correlate all three domains. To address this, I believe the following points are essential. Number of conversion of all information enable the automated recognition of microstructure through modern computer vision techniques, followed by quantitative characterization. The surrogate modeling of the forward relationship among process, microstructure, and properties using ultimate regression models. Here we use the machine learning techniques. Inverse analysis to answer questions such as what kind of microstructure enhance properties, and what processes can reproduce such microstructures. The automation of simulations and experiments to drastically improve data acquisition efficiency. So let's move to the next topic: how computer sees materials. This slide explains a method how to recognize image by deep learning. Deep learning-based image recognition is subdivided into three processes. The first is convolution. The second is pooling. And the third is perceptron. Recent deep learning has more repeated and convolution and pooling layers. Simply speaking, if this convolutional neural network recognition is performed for each small grid, which allows segmentation. The next slide will show an advanced deep learning-based computer vision technique applied to microstructural segmentation. One breakthrough in recent years has been the use of deep learning for microstructure recognition. Here, a UNet architecture was trained with 100 samples and used to segment new images of steel microstructures. As published by the Ajioka, this approach improves speed and consistency compared to manual labeling. Now let's move on to the next topic: how computers diagnose the materials. We know that a healthy bone is dense and strong, while osteoporotic bone is porous and fragile. But to properly diagnose and treat such conditions, it's essential to quantify the state of the bone, not just observe it qualitatively. Microstructure is not just visual. It must be quantified. For example, we measure the grain size and the volume fraction, something like that, and the connectivity of different phases. These can be expressed using descriptors from material science, mathematics, or extracted automatically by convolutional neural network. Here I explain about the topological descriptors and the spatial distributions. In material characterizations, metric features related to length scales, such as grain size, volume fraction, are standardly quantified. However, these alone are often insufficient for comprehensive structural description. Critical properties are frequently governed by topological features, including particle count, connectivity, and dispersion. In a topological context, zero-dimensional features represent vertex information, such as number of particles. The one-dimensional 1D represents the edges, and 2D represents the faces, and 3D represents the volume of the object itself. While particle count is a fundamental zero-dimensional descriptor, materials with identical counts can exhibit vastly different properties depending on their spatial arrangement. Therefore, an index to quantify spatial distribution is essential. Here, we use the Morishita's I-delta index. To evaluate spatial distribution, we employ the Morishita's I-delta index, originally developed in ecology, by dividing an image into Q grids and counting the number of the entries xj in each grid. The index characterizes the distributions. If I delta is larger than 1, that means the particles are clustered or localized. If I delta is less than 1, the particles are uniformly dispersed. This method can be extended to the 3D space by the partitioning the volume into cubic voxels. As shown in the provided example, the left figure yields an I delta larger than 1. That means the uniform distributions, whereas the right figure exceeds 1, indicating particle clustering. Furthermore, a peak value of the distributions reflects the degree of localizations, while the volume associated with the peak represents the cluster size. Next, I will touch the connectivity and the network analysis. That is very helpful to understand branching of the microstructures. To evaluate the entanglement of a matrix and the second phases, branching analysis typically used in biometric fingerprint authentication is highly effective. By recording the coordinates and types of endpoints and junctions, complex network can be characterized. In the case of the 3D dual phase steel microstructures, thinning the algorithm skeletonization revealed the underlying network of the second phase. The number of nodes branching point, like that, serve as a quantitative measure of the entanglement. For instance, the branching density reaches a max at the intermediate annealing temperature, intercritical annealing temperature, providing a structural basis for understanding the strength ductility balance. Also, this is very useful to characterize grain boundary characters. Regarding grain boundary connectivities, the V01 method proposed by Professor Euler at Carnegie Mellon University and Professor Hossein is a potent tool. While percolation theory is commonly used to study phenomena like stress corrosion cracking, the B01 index offers a more rigorous correlation with fractal life. B0 represents the number of connected components, and the B1 represents the number of loops, that means holes. A lower B0 over B1 ratio indicates a highly interconnected network of boundaries. This descriptor evaluates the edge-related connectivity and is thus classified as a one-dimensional topological feature. Next, I will mention about the Euler-Poincare characteristic. For particle connectivity, the Euler-Poincare formula in mathematics is utilized. By utilizing a triangular mesh represent of the particle, the Euler characteristics is calculated from the number of vertices and edges and faces. This is called the Euler characteristics. In topology, the number of holes defines connectivities. This formula allows us to indirectly determine the connectivity of a complex 3D object by relating the Euler characteristics to the number of bodies and the voids. When a more detailed description of particle morphology is required, differential geometry, especially curvature analysis, is employed. This is mainly carried out by Professor Peter Voorhees, Northwestern University before. Also, I learned a lot from Peter Voorhees. At every vertex of a 3D object, the principal curvature, maximum and minimum are calculated to derive the Gaussian curvature and mean curvature. Gaussian curvature is called as K, and mean curvature H. The morphological characteristics are then quantitatively mapped onto a HK plot, HK space, frequency plot. A prime example is the spheroidization of pearlite. The morphological evolution of cementite during aging can be precisely quantified by analyzing the shift in the HK coordinate distribution over time. Recent, very powerful mathematics technique is now coming to the material science field. That is persistent homology. This very strong mathematics, persistent homology, is a new mathematical approach to analyze the shape and the topology of microstructures. It allows us the quantitative features that are otherwise difficult to describe, such as connectivity, loops, and holes, in a rigorous and scalable way. These studies show its usefulness in both optimization and prediction tasks. Okay, we are coming to the deep learning techniques and the convolutional neural network-based image regression for complex microstructures. While the topological descriptors and the persistent homologies discussed thus far are highly effective when the phase can be clearly segmented, as in dual phase structures. They face limitations when they applied to microstructure where segmentation is inherently difficult, such as multensile. In such cases, in image regression using convolutional neural networks, CNN, provides a robust alternative. The fundamental architecture of CNN used here is consistent with standard image recognition models. However, by modifying the output layers from a discrete classification to a continuous numerical output, the model can directly correlate complex microstructural morphology with specific physical properties or process parameters. This framework is formally known as CNN-based image regression. If the fully connected layers of this regression model here, convolutional features are extracted automatically from the input images. These features often reside in a high-dimensional space, sometimes exceeding 2,000 dimensions. Unlike traditional manual descriptors such as grain size, aspect ratio, these round features represent abstract spatial correlation that are not intuitively interpretable by human researchers. Nevertheless, this black box nature allows the network to capture subtle, non-linear structural nuances in multenstic plates or RAS that traditional geometrical analysis might overlook, enabling high precision prediction of materials performance directly from raw micrographs. This figure shows how accurately the CNN estimates tensile strength from a micrograph. For not only a trained dataset shown in red, but also a test dataset shown in the blue, which were not used for training, CNN predicted tensile strengths with accuracy R higher than 0.83 for test data. When my students, Mr. Sawai, demonstrated me this result, I was a little bit surprised and shocked a bit because no traditional metallurgical descriptor extraction was not used at all. Was used to demonstrate microstructural property linkages. Only a computer knows the important microstructure descriptors to yield tensile strength. The convolutional features extracted here through this CNN-based image regression can be regarded as a third type of feature, distinct from conventional material science descriptors or mathematical features. Also, these features span thousands of dimensions and are not easily interpretable by humans. Dimensionality reduction techniques such as principal component analysis, PCA, or UMAP enable their visualization in two-dimensional space. This figure shows a UMAP plot of CNN convolutional features for tempered multensile steels, overlaid with colored code tensile strength data. It illustrated how the computer has identified structural features in the UMAP CNN feature space, where higher positions correspond to greater tensile strength. To facilitate human interpretation of these features, the original microstructure images have been overlaid onto the plot. From the visualizations, one can observe a tendency of higher tensile strength as the second phase becomes more finely dispersed. So from these dimensional reductions, the human being can understand how the computer find out the important descriptors in the CNN image regression models. Next is computers create materials. Both 2D and 3D microstructure analysis are time-intensive. Traditional 2D workflows require heat treatment, cutting, polishing, and measurement, all a laborious step. 3D observation is even more demanding. For example, FIB-SEM imaging can take an entire day per sample. To overcome this, we developed the Genus 3D. Systems are fully automated 3D microscope. This Genus 3D can reduce the processing time for 3D visualization from a monthly task to a daily one. To efficiently acquire microstructure images in both 2D and 3D, experimental automation and microstructure simulations such as the previously mentioned GINA 3D, high-precision cellular automaton, and phase field methods are highly effective. However, despite these advancements in efficiency, this process still requires a significant computational time in practice. Consequently, the remarkable recent progress in generative AI is positioning it as an extremely attractive approach within the material science. Especially in the field of materials engineering, where microstructures images are frequently utilized, image generation AI has become remarkably useful. The foundation of this technology is the Generative Adversary Network, GAN. A GAN consists of two neural networks. A generator here, which creates the fake images from noise. Officially, it is called the latent variables using transposed convolutions. And a discriminator, which attempt to distinguish between the real and the fake images. Through this comprehensive adversarial battle, the system runs to generate highly sophisticated images. Through this competitive adversarial battle, the system runs to generate highly sophisticated images that are realistic yet unique. Another compelling feature is the ability to produce a diverse range of fake images simply by adjusting the latent variables. That means noise. For instance, by applying the finite element method, FEM, to simulate the demonstration of the deformation of GA, again, generated dual-phase microstructure on computers, it becomes possible to obtain massive dataset for microstructures and their corresponding mechanical properties in a purely virtual environment. By performing forward and inverse analysis on these purely virtual data via machine learning, we can propose optimized materials microstructures that exhibit significantly superior properties compared to conventional designs. Recently, research has progressed into generating 2D microstructure images constrained by the specific processing condition using conditional style GAN. Furthermore, slice GAN has been reported, which can generate 3D volumes that maintain the structural consistency. It requires only a single 2D image for the isotropic microstructure, or 3 orthogonal 2D images for the anisotropic ones. Once trained, slice GAN generates a wide variety of 3D volumes by varying the latent variables. Most recently, advancements such as slice GAN Adachi are being explored to incorporate and deflect specific processing conditions into the generated 3D structures. Using slice GAN or slice GAN Adachi significantly reduces processing time for 3D visualization, turning tasks that previously took a full day into tasks that can be completed within hours. Let's move to the final section of my talk. Traditionally, we model materials forward from process to structure to properties. But artificial intelligence enables us to go in reverse, from desired property to find structure to suggest processes. This slide introduces our inverse analysis framework powered by deep learning, as described in our 2024 review. Here. For example, using GANs alone can generate plausible microstructures. But how do we make them optimal? We combined GANs with Bayesian optimization. So it is called the Bayesian optimized GAN to find latent variables that produce the superior microstructures. In this example, we optimize for tensile strength and elongation, achieving a top performances using this Bayesian optimized GAN. In combination with FEM analysis to get the property data set. To fully unlock digital material research, we must rethink the entire experimental pipelines. That means the automating everything from heat treatment to hardness test. It also means building the secure yet easy to use databases and devoting simulation tools that can complement or even replace physical tests. For example, development of fully automated serial sectioning 3D optical microscope genus, just as I described before, to achieve a high throughput output automated microstructure observation. We developed a fully automated serial sectioning 3D optical microscope in 2011. This system revolutionized the efficiency of 3D data acquisition, reducing time required for sectioning 100 layers from approximately 6 months to just a single day. Currently, this technology and the US-developed RoboMet 3D are the two primary systems dominating the global market in this field. The system is designed to perform the entire cycle of polishing, etching, and observation in fully automated sequence. Key technical features include motorized precision stages. The microstructure is mounted on a high precision motorized stage. Here, microstructure, and enabling automated scanning and observation over extensive sample areas. In addition to mechanical polishing, the system incorporates an electro-polishing unit as well. This allows for the successful characterization of chemically resistant materials that are otherwise difficult to etch using conventional method. Through this integrated automation, we eliminated the manual bottlenecks of 3D metallography, providing a scalable platform for high-resolution 3D microstructure reconstruction. Okay, to truly design materials, especially in the context of integrated steel design, we need more than just knowledge. We just combine deep insight into material science with the flexible use of experiments, simulations, and data science, using each where it works best and integrating different approaches effectively. And one more thing, developing a one-of-a-kind research tool or software, somewhere that exists only in your lab, is not just a valuable, it's a truly meaningful contribution to science. And in this talk, I mentioned about the modern metallurgies, but also I also studied about a kind of classical metallurgy before with many peoples over the world. So my research can be categorized into the modern metallurgy I have just described and the classical metallurgies I pursued during the first half of my career. Finally, let me briefly explain this classical methodology and my most recent work. This figure briefly shows my 38 years journey in steel researches. We first investigated how ferrite nucleates preferentially at the corner of austenite grain boundaries. This study helps us understand the role of the grain geometry in phase transformation. Because the corner is a point in 3 dimensions, so it is very hard to find out by the polishing or by a measurement. So we carry out serial sectioning techniques to analyze the nucleation behaviors in 3D. And next, we also focus on dynamic ferrite transformation in collaboration with Professor Peter Hodgson and also Berardi Hossein, and which occurs during hot deformation. We clarified the mechanism and kinetics using in situ observation. And in collaboration with Dr. Dorona, coming from Max Planck Institute, also the Professor Tsuzaki, in the iron 3% silicon alloy, we analyze local lattice rotation within the ferrite phases. EBST helps us visualize the rotation patterns, revealing internal stress and transformation path. And we develop a quantitative method to evaluate the dual phase microstructures focusing on the ferrite and martensite. This was a key to correlating microstructure with mechanical properties. And here's I also learned a lot from Professor Peter Voorhees, Northwestern University, to quantify such kind of three-dimensional microstructures. Also, we analyzed how stress is distributed among phases in austenitic stainless steels during deformation. This clarified how each phase contributes to the overall strength. So like a stress-strain partitioning measured by the neutron diffraction techniques. And here, we present a method to measure stacking fault energies in high nitrogen austenitic steels by the weak beam method of the TM. This value is crucial for predicting the deformation mechanism like twinning. Here, we study the spheroidization process in porous steels during annealing. Understanding this helps improve ductility while maintaining strengths. This result is now written in Harry Badesha's textbooks, Perlite. And also, we characterize nanobainite steels by extremely fine structures. These steels offer a unique combination of the strength and toughness in collaboration with Tim Okina, Peter Hodgson, Berardi. Also, finally, we performed the 3D quantitative analysis of last martensite in collaboration with Professor Morito and also Morris Barclay, and the serial sectioning technique and reconstruction. This gives new insight into the morphology and connectivity of last martensite. Reflecting on this journey, I have come to see that more core pursuit was the quantitative evaluation of microstructure descriptors. In my recent research, we have been working on further accelerating the estimation of three-dimensional microstructure while ensuring the rigorous mathematics foundation. By simplifying particles into the anisotropic ellipsoid to facilitate mathematical handling, we aim to reconstruct 3D models that generate 2D cross sections matching the morphological features of two experimental 2D images as closely as possible. This field is traditionally known as stereology. A key feature of this study is the virtual generation of 150 candidates 3D models and the implementation of a genetic algorithm, GA, to the iteratively search for the 3D architecture with the highest degree of consistency. The extraction of 2D cross-section from 3D models is performed based entirely on the algebraic geometry. In essence, this approach represents AI-enhanced mathematically rigorous teleological method, which we have termed deep stereo. Parallel to this, we are investing in the accuracy with which fracture initiation site in metallic materials can be predicted. By integrating crystal plasticity finite element method CPFM, digital image correlation, and the stress partitioning data obtained from the neutron diffraction, we seek to travel back in time to find out the crack initiation site, to understand the characteristics of the initial microstructure that led to fracture. We are also exploring the integration of deep learning-based image analysis into the temporal reconstruction process. Finally, I would like to express my deepest gratitude, my friends and colleagues in the global steel research community, who have supported and inspired my work over the past 38 years. I am also sincerely grateful to the number of the organizing committee for providing me with the honorable opportunity to deliver this memorable lecture. And I would like to extend a special thanks to Professor Hossein Beladi for his kind personal invitation. With that, I would like to close by expressing my sincere hope for the ongoing development and innovation in the field of advanced steel material science. Thank you for your kind attention. I'll be glad to answer any your questions you might have. Thank you.
Thank you so much, Professor Adachi. Very comprehensive and nice presentation. So I just stop